Hello, everyone, and welcome to the Practical Performance Problem Solving in Jetpack Compose workshop. I'm Tomáš Mlynarič, a Developer Relations Engineer, and I'm joined by my colleague, Ben Trengrove.
Hello. Thanks for staying. We saved the best for last, I promised. So in this workshop, we've got a sample app, we've got some performance issues in it, and we're going to use a scientific approach to first measure, then we'll debug what's going on, and then we're going to optimize and fix those performance issues. And just to call out, this is a slightly more advanced code lab that we're following, where we don't explain the basics of Compose. So if anything seems a little weird, we've got some extra code labs at the end that take you over some more of the basics.
All right.
Cool. Let's get started.
To get started, follow the link visible on the screen, which is google.gle/compose-performance-codelab. Go to the Get Set Up page and download the code base for this project. You can either do it as the starting point zip file, or you can do it with the git command to clone the repository. This repository also contains other code labs. So once downloaded, open the Performance CodeLab project in the latest stable Android Studio version. And if you have an Android device handy, connect it to your laptop, because we'll be using it for running benchmarks. But don't worry if you don't. For this workshop, you can use also an emulator. We don't recommend doing that for real performance measurements, but for here, you can do that. And also, if you wouldn't be able to do any of that, we have system traces that we'll need for analysis available in the same CodeLab website. And while you get set up, we'll have some theory to start with.
So spotting slow, non-performant UI is normally possible just by opening up your app, having a scroll around, and go like, oh, that looks a little janky. But you have to watch out for, especially Compose apps, debug performance is not the same as release performance, so it's not really what your users would see. And you might not have a problem at all. So the first thing we say is always build in release, ideally with R8 enabled. After that, another thing to consider is adding a baseline profile to your app. Because Compose is an unbundled library, it's treated as user code, and that means it can be just-in-time compiled when you open your app. That has a performance price to pay, but a baseline profile helps with that problem. So baseline profiles pre-compile like library code and your code actually at install time of the app rather than first launch. So we've got a graph here that shows the amount of time spent JITting, as we call it, just-in-time compiling, with no baseline profile, with an old baseline profile. So we also think you should try to keep them up to date. Maybe with each major release, update your profile, and then an up-to-date baseline profile. We can see it's much better. Cool. OK, so you've done all that, and you're like, it's still no good. What do I do now? You might be tempted to just dive in and start. You read some blog somewhere or something, and you're like, let's just do some coding. But before that, it's important to follow a scientific approach, or else you're just going to add a bunch of complexity to your app that might not be doing anything. So the first thing to do is establish the baseline by measuring your current performance. After you've done that, you can have a look at that baseline or that benchmark and work out what's actually causing the problem. It's then you can go and start modifying the code based on what you've learnt. And then after you've implemented the fix, we remeasure and we make sure we actually improve performance and repeat. Performance optimization can kind of never end. It's up to you when you think it's going fast enough, but you could keep going forever. So don't, basically. And so if you don't follow a scientific process, you might just find that something improved, something actually made it worse, and you never really know what made the fix in the first place. So to do the measuring, we have a library called Jetpack Macro Benchmark. Basically, benchmarks just run like integration tests. They have some actions you run on your app. We'll see it in this code lab. And they output performance data. In the workshop today, we've already written all the benchmarks for you, so we won't cover how to write a benchmark. But we'll definitely run some so you can see how they work. So with all of that, hopefully you're all set up, and we can get started.
OK. So I have the project here in Android Studio already open. And I'm going to build it so that you can see how the project looks, and also go over the just a brief, like from top, how it looks. So I use the project view in the project pane so that I can see the modules and the build Gradle files because we'll need it. And I have the app module here that will be making the changes to the code. So this is basically the Compose app that we built. And then we have a measure module, which contains the benchmarks that we will be running to measure the performance. And the app looks like this. It contains several tasks. Each task screen has a different performance issue, and we'll basically go one by one and start fixing them in this CodeLab. The first task basically is a list of items of lazy grid, and each item has some title, image, and then some like published date that with a current time zone that's formatted in a current time zone or in Prague time zone on my device, and we will see that in action. How we'll fix it later. All right, so to analyze performance, we can use system tracing. And so Compose automatically gives you some information on what phases it runs in, but that is not enough to get like a full analysis. So to help with that, we need to enable composition tracing. And so you do that by adding runtime tracing dependency to the app module. So I'll go and add it into the build.gradle file in my app module. I will add it here. And at this point, if I would run a system tracing profiler from Android Studio, I would already get the composition tracing information. But we want to use benchmarks to also measure the performance. So we need to add two more dependencies, which is tracing Perfetto and tracing Perfetto binary to the measure module. Don't add this to the app module.
Yeah, these dependencies are like massive, so don't accidentally ship them with your app. Only add them to the measure module.
All right, so I added it here. And the last thing to have composition tracing enabled with benchmarks is add a test instrumentation argument to the measure module. So just copied it here as well, and I'll add it to the default config block. Then I'll sync the project, and I'll be able to run the benchmarks. So now it's syncing. No. All right, it's synced now. And so to run the benchmarks, we'll go to the measure module and find the accelerate heavy screen benchmark. And from here, we can basically just tap the run icon in the Gutter action and run it. And this will run it on the device I have here physically ready. And in the meantime,
so the benchmarks in the project, just to save time, are only set to run with one iteration, which is not what we normally recommend. We think you should probably run them with at least 10. And what that's doing is averaging out the results, because a lot of things can affect performance. The device might get too hot. You might get a push notification in the middle of the test. All of those things have an effect on the results. So by running the test over and over again and averaging it out, you'll get a more reliable result. The other thing is we're using compilation mode full for these benchmarks today because we're interested in runtime performance. What that does is just fully compiles the app in advance, so we're not going to get caught out by just-in-time compilation. But actually, if this was a startup benchmark, that would slow things down because we would have to load all that pre-compiled code from disk, and that would actually slow down the performance at startup.
Yeah.
So it looks like that finished.
Yep, we're finished. We have the benchmarks. So whenever the benchmarks are run from Android Studio, you'll get the outputs in the Android Studio output pane, and you'll get some metrics on what it measures. So the interesting things here to measure runtime performance, that means like how smooth it is, are the frame duration and frame overrun. So the frame duration metric basically tells you how long it takes for your app to produce the frames, and it gives the results in a statistical distribution. Basically, the lower the number, the better the smoothness of your app it is. The frame overrun metric, on the other hand, tells you how much time there was still the frame limit. So a negative number is basically a good. There was still some time until the frame limit, but a positive number, like we have here in the 66 milliseconds, that means that this went 66 milliseconds over the limit that the device expected, and therefore this screen definitely junked and was not smooth enough. And so there are some other metrics we have here. You can add as many metrics as you want, and all of these basically are here to help you understand the performance of your app. So I have the image placeholder, and I have it added here with a trace section metric, and basically I can get more understanding if I'm going into the right direction. Okay, so once we have the benchmarks ready, the benchmarks actually produce system traces, and we'll use the system traces to analyze performance. You can analyze it either with Android Studio Profiler or with a browser-based tool, Perfetto, and we'll use that here. So to do that, you just go into your favorite browser and go into ui.perfetto.dev. And it will load the tool to analyze performance. And the system trace, for you back to Android Studio, is located in the build folder of the measure module. I'll go there, outputs, connected Android test additional output. Then there's the build type that it was run and the device name. So my device is Pixel 6. And here you would see all the system traces for each iteration. So here we run only one iteration, so we have only one Perfetto trace here. And from here, I'll just drag it and drop it into Perfetto. And Perfetto will load all the information in browser so we can analyze it there. At this point, if you can't really run the benchmarks, you could go to the Get Setup page, and here are all the traces. So here's the step 1. This is the first benchmark. You could download it here and just drag it into Perfetto for analysis.
So that's a lot of information.
That's a lot of information. But don't worry. Perfetto basically records everything that's happening on your device during the trace. But you don't need all these informations to analyze performance of your app. So when you load Perfetto, first you would see the state of the CPU, state of GPU, and stuff like that. And then you would see a list of processes that were running during the trace. But when you analyze your performance, what you're interested in just your process. So in our case, that's compose-performance. And so I can just click it and unroll a list of threads that were running inside my process. So it starts first with a main thread, then render thread, and then the rest of the threads that were running during the execution of the app. And then, so navigate within Perfetto. You can use WSAD to zoom in, zoom out, go right, left, because we think performance analysis is like playing a game. And so that's how you navigate. So to start with analysis, you need to understand the expected and actual timelines. So the expected timeline here, the first one, tells you basically when the system expected the frames to be produced. So here we can see that each frame takes 16.6 milliseconds, which means that this device runs in 60 FPS. If you have a device that runs in with more frequency, you could see shorter duration here. The actual timeline, on the other hand, tells you the actual duration of the frames that the app produced. There might be different colors here, like a green frame here, which means it takes 3 milliseconds to produce this frame. That's all good. There was no junk. Everything's fine. But you might see red frames, like here and here, that these are the frames that took longer than the device expected them to be created. And these are the frames that you should really invest into what's going on. The first red frame here is the startup frame, and so the app startup usually takes longer than 16 milliseconds, so we will not go there. But then there's another red frame that takes 89 milliseconds, and that's during the execution, and that's our janky frame. All right, so to analyze, we found the janky frame, and we need to go there to analyze what's going on there. So to first do that, we need to understand how the Perfetto organizes the sections. And basically, it means that each bar from top, like here the compose, recompose, which is populated by Compose framework, by the way, is, so each bar from top down is the total time of the bars below it. So if I would zoom in a bit more, we can see that there's some lazy item creation. And then in this item call, we see that we would have some publish date format and image placeholder, some async image, and other stuff.
Yeah, so basically, it's a stack trace. That's just showing you all the functions in the order they were called and the time it took. But what about gaps? I can see a few gaps in the trace as well.
Oh yeah, here are some gaps. So the gaps mean basically that there was some code running, like untraced code running. That just means that the system trace doesn't have enough information. This doesn't mean that the code wouldn't be running. So in system tracing, it means always there was something executing. It's just that the trace doesn't have enough information to tell you what was running in the gap.
OK, cool. But how do we use all these like fancy colored bars to work out what's actually wrong?
All right. So to get basically as a first step in analysis is like you need to look out for anything that's suspiciously long, any section that takes longer than maybe some others, and you start there. So in our case, it sort of looks obvious that the image placeholder takes 19 milliseconds, which is it takes longer than even one frame. So this is where we'll start. And so the image loader uses the painter resource, loads some JPEG, decodes it, and shows it on screen.
Yeah, so like it's really obvious to always load network images off the main thread. But watch out for the placeholder as well. Your placeholder is generally loaded on the main thread, and it might just be way too big and causing just as much jank as just if we'd loaded the network image from the main thread. So like possible fixes, well, we'd have a look, make sure if it's too big, we could shrink it, or maybe we could use a vector drawable instead.
All right, so let's fix it in our code. So I'll go into the app module and into the accelerate package, accelerate heavy screen. And here, basically, the screen is, collects some items from the view model and loads a content. It shows the lazy vertical grid of items, and then I have the heavy item, which contains some text, published text. This is what the UI shows. Async image, and here's the placeholder. And so basically, the placeholders, I was saying, it's 1600 by 1600 resolution, so this is clearly too big for what it shows. And so the fix here is, well, easy. We can just use vector here, save it, and that's done. So let's verify it. So to verify if we actually fixed it, we'll run the benchmark again. So we go into the accelerate heavy screen benchmark, run it from the gutter action icon, and wait for the results.
Yeah, so watch out for image placeholders. They generally are loaded on the main thread. But this was just an example. We wanted to show you what like a really heavy bar in a trace looks like. You might spot something completely different, but this is kind of how analyzing traces work. You just got to dig in, look for things that look suspicious, and go and read the code and come up with a hypothesis and make a change and see if it fixes the problem. Cool, looks like it's loaded.
Yeah, it's now running, so it's swiping the content. And I've got the results. And so again, as before, I have the same results in the same folder in the build folder of the module. So now I'll go, drag and drop it into Perfetto, and see how it helped. So I'll find my process name, compose performance. I'll zoom into the second janky frame, second red frame, and I can see that the image placeholder now takes 700 microseconds. So it's clearly like 20 milliseconds improvement.
All right, so we definitely made it better, but that frame's still looking pretty janky to me.
Yeah, it still takes 92 milliseconds. All right, what's happening here? If we could, another thing is same process. Find something that's taking time on a main thread that doesn't have to be there. And so in our case, there's this a suspicious binder transaction that is 1, 2, 3, 4, 6 times, and it takes a millisecond What's a binder transaction?
So binder transactions are just when your app has to talk to something outside of its own process. Basically, it's talking to the system. They can be like lots of different things, like say requesting a runtime permission. I think even logcat is a binder transaction. Just anytime your app has to talk to the system, it goes through one of these. Unfortunately, they don't really tell you what exactly they are. You just get this label binder transaction. So what you have to do is look at where it is in the trace and come up with an idea of where that roughly might be in your code, and then you can go to it and wrap it in a custom trace section, and that will give it a label. And you can use that to verify you've actually found the right transaction.
All right, so let's go in and fix it and get more information. So I'll just hide all the panes and go into the accelerate heavy screen as before. And, well, I need to look into something that's calling a system service or something. And bam, we have it here, register receiver. Who would say? So to verify, if this is actually the cause, I can add trace call and wrap it with a label. So I have the trace section metric here prepared with the same label, so I'll use that here. And if I would rerun the benchmark, I would basically see that these binder transactions actually correlate to this call. To save some time, I'll not go through that path and go directly to fixing that. So this is on a main thread. So to offload it over a main thread, we can use coroutines. So let's go and get a scope by remember coroutine scope. And then we'll just wrap this in scope.launch. And we'll use a different dispatcher than the main dispatcher. So let's use IO here because it's talking to the system. So if we do that, we will basically offload it from the main thread. But it was there 6 times. Yeah. So there's still unnecessary work happening here. And we're using it for the time zone changes. And time zone is the same time zone on all the, like across the whole device. So we can hoist it. And so to hoist it, there are 2 ways. We could either pass the parameter along the tree, but in this case, it might actually make sense to use a composition local because it has it can have very well defined default value, and it can be used only in the place that we need it. So we'll use the composition local. So I'll help myself and go into the page 6 and find we have the composition local here, so that I don't have to remember the exact syntax. So I'll paste it. So basically, I'm creating a composition local off with the default value of the current system default. And then I need to provide it. So I have a prepared provide current time zone method here. So I'll use the composition local provider that comes from the Compose framework. I have the imports, and I don't have the value. So now I'll just go to the published text composable that is, in every single text of every single item. And I'll just take that from here and put it here. Conveniently, it's named the same. And so I have that, but I have an error here. So here I'll just use the newly created local time zone.current. So whenever that composition local is changed, basically this composable will be recomposed with the current value. And so the last step is this isn't used anywhere. And so composition locals only work for the subtree of where you call them, the providers. So this is usually you would use it in like a root composable of your screen. So in my case, I'll do it in this accelerate heavy screen composable. And that's it. And basically, in these composables, this composition local will exist. Nothing will complain, and we can verify if we fixed it. So we'll go back into the accelerate heavy screen benchmark and run it from the gutter action.
Yeah, so binder transactions are perfectly normal. There's no need to be scared if you see one. But a lot of them can actually be offloaded the main thread. The way you can tell, actually, is if they use an activity context, they have to stay on the main thread. But all the other ones in general can be moved to a background thread. So we'll wait for that to finish.
Starting the benchmark. Now it's running. and we've got the results. So same process. We have the system trace here. Let's drag and drop it into Perfetto. Follow the same process and find our here. Zoom in, and we can see that there are no binder transactions here anymore.
But we still used it, so where did it go?
Yeah, that's true. We can use the search bar here. So I named it as a publish date register receiver. I'll just tap enter, and as you can see here, we have just one occurrence of this section, which is here. We still see that this is the binder transaction, but only one during the execution, and we can see that it uses a default dispatch thread that is created by the coroutines. So we offloaded it from the main thread.
Nice. If we scrolled back up and had a look, we could see the frame is actually still janky. There's one more performance issue in that task, but just to save time in this workshop today, we're going to leave that one as homework for you. That's step 7 of the CodeLab.
Right, and also it might make sense to not use that in the composable and offload it like in a data layer to register in the broadcast receiver. But keep in mind, even though that it's in the data layer, it still be running in the main thread. So just to call that. All right, so since we skipped the unnecessary subcomposition task, let's go and compare the result and finish the cycle of measuring initial performance, fixing it, and now comparing if we actually improved it or not. So in this code lab, we'll just do like very simple comparison. We'll go into and take the results here. I'll just copy paste it here into the code so I can see it in the same space. But I can use the test history and find the result, the first benchmark that I was running. So that's my before state and after state. And I can see that first it was running actually faster in many cases. But in the P99, it got pretty close. And
yeah, we've been caught out by the one iteration. So if we ran this benchmark 10 times, you would see that it did get faster.
Yes.
But which we also saw in the trace.
Yeah,
so yeah, that's why we say don't run them just once. Run them 10 times.
Exactly. But yeah, that's how you can simply compare and verify that it actually helped with the performance.
Cool. So for the rest of the workshop, just to save time, we're not going to go through the full cycle of running the benchmark, working out what's wrong, and stuff like that. We're definitely convinced that that's the best way to optimize performance, though. So if you're doing this at home, we encourage you to run the benchmark first. We've written benchmarks for every task in this code lab so that you don't have to do it and you can run them. All right, cool. Moving on. So the next thing we're going to look at is preventing unnecessary recompositions. And while you might get set up, I'll just go over a quick bit of theory that will help understanding this section. So Compose has 3 phases. Composition determines what to show. Layout determines where to show it. And drawing, I'm sure you can guess, draws it all to the screen. The cool part is that Compose can actually skip a phase if it doesn't have to do anything. So if we can avoid, say, changing our composition tree, we can skip composition altogether. And composition generally is the most expensive phase of Compose. That same thing applies to layout and drawing, though. Like if you don't invalidate the layout can be skipped. And if somehow you don't, you can even do composition and not require a redraw. They're all skippable. So let's have a look at how you might actually go and do that. So we'll open the phases compose logo file in the app module. So it's under phases, phases compose logo. I'll close that so we can see. And I'll run the app so we can see what's going on. So this is task 2. I'll open the layout inspector. The layout inspector is a tool that shows you what in your screen is recomposing. And we can see here that whenever we see this blue box, that's a recomposition. So this task is like just that logo is bouncing around the screen, but we're not actually changing what's being shown on the screen, right? We're just moving something. So surely we can do that just using layout. If I expand the layout inspector, we can see that this phases compose logo is just going to the moon, straight up. We can definitely do better here. We're wasting a lot of performance. So let's have a look at how we might do that. having a look at the code, this is the function that we saw recomposing a lot. And we have this logo position. You don't have to dive into the logo position function, but we just need to know that it returns the next position for the logo, and it does it with a compose state object. And now anytime a compose state is read, that's how compose knows when to recompose. So we're reading this state here, and so anytime logo position changes, compose will recompose the nearest recomposition scope, which in this case is this whole function. And so all of that code is being rerun for every time logo position changes. So to fix that, we need to defer when the state is being read, and there's actually a really easy way to do that in this case. We can use the offset modifier that takes in a lambda, and we can just actually pass the state straight in because it's an int offset. And now this lambda here will only be called in the layout phase, and that's where our state read is. And so now we're not going to recompose, we're just going to invalidate layout instead of invalidating composition. So I'll rerun the app and we'll see if it worked. So we can already see that the blue box isn't showing up anymore. And if I expand here, we can see no more number skyrocketing to the moon. We're just relaying out now. We're not actually recomposing. So the only code being rerun in our file, at least, is just that.
All right. So there are also other Lambda-based modifiers. So for example, if you want to animate background or something like that, you can just call draw behind with draw right and the color. This way, you would also skip the layout phase and only redraw. Same thing if you want to change alpha or rotate or scale. You can use the graphics layer modifier with the Lambda version, and you can even combine all of these into just one modifier. But what if there isn't modifier? What if I want to change size or something?
Yeah, so there won't always be a Lambda version of the modifiers you're using, and in that case, we can fall back to a lower level API, which just happens to be what we do in the next step, step 10. So you can implement a custom layout, and that means any state reads inside that layout composable will only invalidate layout. And you can even go directly to draw. You can implement a custom canvas. If you can get away with just using draw calls, that would be very performant. So that is also a possibility. In this case, we'll just do the layout. So step 10, and we'll open up the phases animated shape file. So I'll close this for the moment, just so we can see the code. So this is task 3. And this one, we have this button here that when we tap it, there's just like this animating circle. It has a nice spring effect. But we can see the same problem as before. We're recomposing on every frame. Again, we're not changing what's actually being displayed on the screen. We're just resizing. So we know we can do better. So let's give that a go. All right, we'll have a look at the code. This is the my shape composable, which is the circle. And it takes the size input here, and that's what's changing. So we'll have a look at how size is created. And size is an animated DP. So anytime size changes, which will happen every time we click the button, this whole function has to recompose because we're reading it here. The nearest scope is here. So all of that's rerunning, and then my shape gets recomposed. So the first thing we can do is just defer that read. And we can do that by switching size to be a lambda. And I'll update my call site. But here, I'm like, OK, cool. Maybe I can just switch that to a lambda. But no, it doesn't exist. So in this case, we're going to have to implement a custom layout instead. And just to save myself a bit of typing, I'm going to copy it from the CodeLab. So I'll paste in the new implementation of my shape, which uses the layout modifier. And we're using that because we only have one thing to lay out. You can use the layout composable instead. The same theory applies, and you do that if you had multiple composables to lay out at the same time. And so now, this is where we call the size lambda. And that means that's where our state read is happening. And because we're doing that inside this layout, this is now our nearest scope. And so only this will be rerun when size changes. We then just take the size, make some constraints, measure, and place. You can learn about making custom layouts in our documentation. Cool. So I'll rerun it. We'll see if it worked. be nice to me.
Layout inspector is tired.
Yeah, it's been a long day. Hey, there it is. So now I'll tap the button, and we can see, yeah, problem solved again. We've still got the blue box around the whole thing, because the button still recomposes on tap, but we can see the circle now, no number. It's just being skipped every time. Cool.
Great. So remember, you shouldn't have to recompose only when you adjust layout on a screen, especially during scroll or animation. And this might lead to junky frames sometimes. So recompositions that occur during scroll is almost always unnecessary to occur and could be avoided. So that's how you fix performance. All right? So we fixed unnecessary recompositions with differing the state. But we can also fix unnecessary recompositions with stable classes. And so that's what we're going to do in the last part of this workshop. So we will not use layout inspector in this case. We go into tasks 4, and we see a list of items here. So when I interact with the screen, we're using a modifier that shows a border whenever something recomposes on a screen. So we can see here that when I'm adding more items, like this recompositions goes through the roof, everything recomposes. And we have different types on a screen here. So we have items marked with the ref icon, with the blue ref icon. And these items basically simulate a situation that you might have in a code base, like when SQL creates new entities, like the room database, or the APIs entities are recreated, like from Firestore or any other, whenever there's there's parsing from JSON or something occurring, because this is where the new instance is created and provided. So that's the ref icon. And the EQ icon, items marked with these usually stay the same during this execution. Only when I change actually that instance, then it's recreated. It uses the copy method just to simplify it here on the screen. And yeah.
So the way skipping works in Compose is actually generating a whole bunch of code inside each of your composables. And what that code is doing is it's looking at the current value of each parameter that's passed in, and it's comparing it to the previous value. And that's how it knows if it can be skipped or not. If all the parameters are equal, then that composable won't actually be rerun. But the trick is it only does this if all of the parameters are what we call stable. So a stable type, what is that? It's when it's either completely immutable, or Compose can tell when that object has changed, which normally happens via a mutable state of. If it's not one of those, we consider it unstable. And that means we won't generate any skipping logic in that composable. It will always be rerun. So unstable classes tend to happen when the class itself is just straight up mutable, like you might have a var property. But more commonly happens because it's in an external module. So we can only determine the stability of classes in modules where the Compose compiler is actually run. And this includes things like Java standard library functions, which we'll see soon. But also maybe you've just got a generic Kotlin data module or something. Those classes will be considered unstable. The other thing is this nest. So if you have a class that contains an unstable property, well, that parent class will also be considered unstable. So the first thing you can do to help with all of this stuff is just to enable a new thing we're calling strong skipping mode. And with strong skipping mode enabled, even composables with unstable parameters are now able to be skipped. So that should just radically simplify dealing with these sort of issues. So definitely recommend doing that first. The other thing is, if you've ever found yourself, you've already been dealing with this in the past, and you're wrapping Lambda calls with remember, well, strong skipping mode fixes that as well. All lambdas in composables are now remembered for you, basically. We're just wrapping them all with remember ourselves. How does the skipping work? Unstable classes are compared using instance equality. So if the unstable class is the same exact instance as the last time that composable was run, then the composable will be skipped. Stable classes are still compared using the equals method.
All right. So let's go and enable it in our code base.
Nice.
Nice. So we go into the build.gradle file of our app module. I'll just close this here. And we can enable it in the new Compose compiler plugin that comes with the Kotlin 2.0. And basically, this plugin will simplify all the setting up of the Compose thing. It will prevent all the juggling between Compose compiler version and Kotlin version, and therefore, it'll always be compatible. You don't have to, so you can also use skipping mode before Kotlin 2.0. It's just named a bit differently and set up a bit differently. So to enable that, I'll just go and set true. I'll sync the project and rebuild my app to see what effect it has on our list of items. So now I'll just go and add a bunch more items. And I can see that conveniently, every other item is only recomposing. That's just by enabling the strong skipping mode. In our case, the items marked with ref are still recomposing because they use a new instance with every change. So let's see what item it is and why the reason of that is. So I'll go into the stability package here, and I'll go into stability view model. And basically, the stability item data class here is what is shown on the screen. So it uses a parameter string idle, like a primitive type, like int, string, boolean, or it uses the stability item type, which is an enum, and enum is considered stable. But the local date time is coming from the Java time package, and that's a Java standard library. And that's a module that doesn't have dependency on Compose compiler. So in this case, to make this class stable and use the equals call instead of the instance check to basically help with the stability here, I'll just need to change my language. And then I'll just annotate it with immutable because, well, this class is basically immutable. I'll rebuild the project and see if that helped. Yep, rebuilding now, and we'll see, that. And OK, and now when I go and add a bunch more items, we can see that nothing recomposes.
I mean, no, there's still one thing recomposing there.
My site is bad. Yeah, the latest change. OK. All right, so the latest change here, let's figure out why it's still recomposing. So this is the stability screen file. I'll go here. And so the UI is straightforward, some items from view model, some column, lazy column with the items, and here's the latest change composable. And it shows the change, the text. And the input parameter is a local date. And guess what? It's still standard Java standard library, Java time package. But the problem here is I can't really annotate this class. Oh, well. So in the past, we were recommending that you would need to wrap this class with your own class and annotate that class as stable or immutable. But there's a new way to do that. And we can do it with a thing that we call a stability configuration file, which you can enable in the build.gradle as well. So we'll go to the build.gradle file of the app module or of the module that you want to enable it in, and I'll just add stability configuration file. And because I don't remember the syntax of resolving a path in Gradle, I'll just copy paste it from the codelab. And so basically what it sets is it tells a path of a file in your code base that will contain information about which class do you want to consider stable. So I have the stability config file already created here in the root folder. And now I just need to add the class that I want to consider stable, which is java.time.localDate. All right, I'll rebuild the project, and I will run it. And I'll see that this should fix the problem.
So you can also use wildcards in these stability configuration files. So we could have just written java.time.star here, and that would have also fixed the last issue as well. But maybe you could consider, like if you've got a generic Kotlin data module, you might want to put whatever your app's name .model.star or something, and that would declare your whole module stable. Just keep in mind, it's not actually making it stable. It's just you're like opting into the contract to say, we write immutable data modules, so please just consider the whole thing stable.
When I interact with the screen, I see that only when I check the item that changes, but when I add new items, remove items, nothing recomposes.
Cool. So it looks like it's totally solved. So yeah, quick recap. First thing to do, enable strong skipping mode. Hopefully it makes this all much easier. We're actually going to switch it on by default really soon, so you might not even have to enable it. And then the other thing is check out stability configuration files. And with that, that brings us to the end of the CodeLab. So we only showed you a small portion of like the things you might run into in the real world, but we hope the techniques we showed are generic enough to apply to whatever situation you end up in. If you found this interesting, here's some more CodeLabs. We've got how to write benchmarks, if you want to learn how to write those benchmarks, how to add a baseline profile to your app, and of course, just our compose performance documentation.
All right, and that being said, we thank you for your attention, and now go and compose a performant app.
Thank you.